Welcome back everyone. We can discuss some gate questions based on an important topic, that is a combinational circuit, that is the multiplexer. So before that, these are some important basic points regarding this multiplexer. Multiplexer is a combinational circuit, has maximum of 2 raised to n data inputs, n selection lines and a single output line. One of these data inputs will be connected to the output based on the value of the selection lines. Always these multiplexers are associated with single output line. And among the 2 raised to n inputs, at a time we can pass one among these 2 raised to n inputs to the output line, and this passing is based on the current value of our selection line. Okay, so here it is at 2 by 1 mux. 2 by 1 means 2 inputs and 1 output. And for representing this 2 by 1 multiplexer, number of input here it is 2. This 2 is equal to 2 to the power 1. Means here we need only a single selection line. Okay, based on the value of the selection line, we can properly pass one among these 2 inputs to the output line. That is, if the selection line value is equal to 0 now, then we can pass or connect this input 0 to the output line and block this input 1 and in that time. And if the selection line value equal to 1, we can connect or pass this input 1 to the output line and we can block this input 0 at that time. At a time, we can pass only one of the input to the output line. And this passing is based on the current value of our selection line. And here it is a 4 by 1 multiplexer. One output with 4 inputs. 4 is equal to 2 to the power 2. The power is 2, means we need here 2 different selection lines like this S1 and S0. Based on these values of the selection lines, we can pass one among these 4 inputs to the output line at a time. If S1, S0, the value is like this, 2 selection lines. So what are the possible combinations for the selection lines? 0, 0, 0, 1, 1, 0 and 1, 1. If this combination is like 0, 0 is equivalent to 0. So input 0 now connected to the output line if the selection line combination is like this. In that case, it blocks all other 3 inputs to connect to the output line. All these 3 inputs are blocked now and only passing input 0 to the output line whenever the selection line value is like 0, 0. If it is like 0, 1, S1 equal to 0 and S0 equal to 1, which is equivalent to 1. So in that case, this multiplexer connect input 1 to the output line and block input 0, input 2 and input 3. And if the selection line combination is like 1, 0, so this is equivalent to decimal 2, right? So in that case, this multiplexer connect input 2 to the output line and block input 0, 1 and 3. And similarly, if the selection line is like 1, 1, decimal, which is equivalent to our decimal value 3. In that case, it connect input 3 to the output line and we can block, or this multiplexer block other 3 inputs. So this is the basic working principle of a multiplexer and this is a combinational circuit. So consider some gate questions. Consider a 4 to 1 multiplexer with 2 select lines S1 and S0 given like this. Okay. Thus, selection lines are assigned with variable or input P and Q, and here 4 inputs are there, 0, 1, 2, 3, 4 inputs. The 0th input line is assigned with an input value 0. The this first input line is assigned with an input value 1. Second input line is assigned with an input value R, and third input is assigned with a value R bar, and selection line S1 is assigned with value P, or S0 is connected with Q, and this is the only one output line. Okay, so these are the different possible combinations for our selection lines. 0, 0, it can be represented using this P and Q variable like P dash Q dash. 1 is represented P dash Q. 2 is represented PQ dash. 3 is represented PQ. Okay. So the minimal sum of product form of the Boolean expression corresponding to this multiplexer. The minimized SOP form we needed here. Okay, that is the expression corresponding to this output line F we need to identify here. So that is here, if P and Q, this S1 and S0 is equal to 0, 0. In that case, this multiplexer connect the 0th input to the output line. How to represent that particular case in a SOP form? That is P dash Q dash 0. P dash and Q dash and 0. Okay. Then the next term, how to connect input line 1 to the output line. For that, we need the selection value like 0, 1. 0, 1 means P dash and Q, and this one, P dash and Q and 1. Plus, now we want to connect our line 2 with the output. How? For this, here we generate the binary equivalent corresponding to 2. That is, here we need 1 and here we need 0. That is P and Q complement. And R. In input line 2, it is connected with R. So, P and Q dash with R. P and Q dash and R. And for passing the line 3, input line 3 to the output, we need the selection value like 1, 1. That is P and Q, and for the input line 3, which is connected with the variable R complement. So, P and Q and R complement. Okay, so this is the detailed expression generated directly from this given multiplexer or given information. Now, consider this expression. AND operation with 0 is always 0. So, this term becomes 0. AND operation with 1 is the term itself. So, this term becomes P dash and Q. So, we can remove this term, and now it is P dash and Q plus P and Q dash and R plus P and Q and R dash. This term is not directly present here in this given options, right? So what we want to do next, we need to simplify this in order to make this one matching with one of these 4 options. Okay, for that we can consider like this. That is, keep this term as it is, P and Q dash and R. And from these two terms, take Q outside. And this becomes P complement plus P and R dash. Okay, so inside this bracket, we can apply the distributive law. Now it become this term as it is kept here. Next, Q, this Q. While applying this distributive law over this part inside this bracket, this become P dash plus P and P dash plus R dash. We know that this P dash or P is always 1. Okay, so we can substitute 1 instead of this. That is 1 and P dash plus R dash. So this become Q and with 1 is the term itself. So Q and P dash plus R dash. While distributing this Q inside the bracket, it become P and Q dash and R plus P dash Q plus Q R dash. So now this option is available here. P dash Q plus Q R dash plus P Q dash R. Okay, so option A is the right answer. So after generating the detailed expansion for this output function f, try to simplify this in order to make that simplified form comes in match with any one of the given option. Okay, so after the simplification here, this generated form comes in match with option A, so A is the right answer. Okay, consider another one. Consider the following combinational function block involving 4 Boolean variables x, y, a, b, where x, a, b are the inputs and y is the output. So the function is like f with arguments x, y, a and b. If x is equal to 1, then y equal to a. So y is the output line. Else y equal to b. Only single output. If x value become 1, assign a input to the output y, and x value not equal to 1, then assign b input to the output line y. So based on this information, which one of the following digital logic block is the most suitable implementation for this function? Options: full adder, priority encoder, multiplexer or flip-flop. So from this it is clear that only one output line, that is y. Y is assigned with A or B inputs based on the value of this x. If x become 1, A input is assigned with y. If x equal to 0, B input is assigned with y. That means this is actually a function or working of a 2 by 1 mux, like this. If x value become 1, A is assigned to y. If x equal to 0, B is assigned to output line 1. So the correct logic design explaining this operation is our multiplexer. Okay. Another question. Consider the circuit. Different variables are like x, y bar, a set, x and y with 2 multiplexers. First multiplexer is a 2 by 1 multiplexer. Its selection line is a set, is connected with a set. And the inputs to this multiplexer are x and y bar. Its output is connected to the 0th input of our second multiplexer. The second multiplexer's first input is x and its selection line is connected with y. Okay, consider the circuit thus. Which one of the following options correctly represent the final output function? That is, identify the correct expression, simplified expression corresponding to the output of our second multiplexer. So first identify the detailed expansion for this circuit. So that is first case. Our first step is identify the output of our first multiplexer. That is, if the selection line here it is Z, if Z equal to 0, the output become X, and Z equal to 1, output become Y bar. That is Z complement. Z complement means Z equal to 0. If Z equal to 0, then X is the output. Z complement X plus, if Z equal to 1, Y dash is the output. So Z Y dash. So this is output of first multiplexer. This is taken as the 0th input of our second multiplexer. Okay. So this is the 0th input of second multiplexer. Based on this selection line Y of our second multiplexer, if Y equal to 0, this is the output. And Y equal to 1, X is the output. So write the detailed expansion like this. Y dash means Y equal to 0, then we need to pass this particular input as the output. So Y dash and Z dash X plus Z Y dash. Plus if Y equal to 1, X is the output. Okay. This term is not directly present in this option. So we need to simplify this. So we can expand or distribute this Y dash here. Now it become Y dash Z dash X plus Y dash Z, Y dash Z and Y dash. That means Y dash Z itself plus this YX. Again, this particular simplified form is not directly available. We need to simplify more. More than one simplification is possible here, but we need to get the exact or the correct one that will match with the given option. So for that, consider this X common to this and this. Okay, so take that X out and become Y dash Z dash plus this Y, and keep this term as it is here. Now we can distribute this OR here. So it become Y dash plus Y and Z dash plus Y. Y dash plus Y is actually 1. So it become X and 1 and Z dash plus Y is Z dash plus Y itself. Plus this term. So now take this X inside, that is X Z dash plus X Y plus Y dash Z. X Z dash plus XY plus Y dash Z. Now our simplified term comes in match with our option A. So this is the expression corresponding to this F, that is the output of our second multiplexer. Okay, so these are some gate questions based on multiplexer. In our next video also, we can discuss some more gate questions and tricks to solve questions regarding this multiplexer. Okay, thank you.